Hello, my name is Sean Parker, and this is my screencast for my project Reinforcement Learning in Classic Arcade Games. So, what were my project's aims? My project was to create a reinforcement learning agent that could play 3 different Atari 2600 games, Pong, Breakout, and Space Invaders, and also to create a visualization of the internals of the trained agent so we could see what it was learning and what information the agent was focusing on in order to play the games. First, we'll describe what reinforcement learning is and how it works with Atari. On the left-hand side, you can see the model of reinforcement learning, where you have an agent and an environment, where the agent takes some action in the environment, which produces a new state and reward for the agent. On the right-hand side, you can see the model of a convolutional neural network and the fully connected network, which acts as our Q function approximator that will say how good we think an action is, given the input state. We have 4 possible actions for Atari: no op or no operation, fire, left, and right. We combine both of these ideas into what's commonly known as deep reinforcement learning, where the agent is our neural network and predicts our action based on the input from the environment. Now we'll take a look at the Atari network in a bit more detail. The objective of the game is to maximize the score that you can see on the top. The input from the emulator is 210 by 160 pixels, but we need to resize that to 84 by 84 pixels as the square input to the network. In this project, we investigated 3 different methods, those being deep Q networks and double and dueling Q networks. The output of the network is an approximation of the Q function. It says how good we think a specific action is given a state. Then we take the maximum of these outputs, which predicts our next action. Just using a single frame in the forward pass of the network, we won't be able to tell the direction of the ball, but a history of 4 frames allows us to determine the direction of the ball. Now we'll discuss the results for the 3 different environments and the different methods that we investigated in the project. First, we'll look at Pong. With only 100,000 frames of training, the agent still hasn't learned to hit back the ball, and it only happens by chance. After 2 million frames of training, the agent has learned to move towards the ball, and it is hitting it back more frequently. However, the opponent still wins as we don't move under the ball in time. After 5 million frames of training, we always manage to move under the ball and beat the opponent every time. Now we can look at some of the results from training. All 3 of the methods reach a score of around 20 after about 5 million frames, eventually converging to the perfect score of 21 after 10 million frames. Since all 3 of the methods converged very quickly, it shows that Pong is the simplest of the environments, and that's why we used it to test out the methods initially. Next is Breakout, and after 1 million frames of training, we can see that the agent has learned to move under the ball, but it doesn't always hit it back perfectly. After 10 million frames, the agent has learned to move under the ball, and we hit it back with more frequency. However, we do still make some mistakes, and over the next 10 million frames, the agent will learn how to move under the ball every single time. Now, after 20 million frames, we can see that the agent is hitting the ball back nearly every time, and it's beginning to develop a strategy where it tries to tunnel in one particular spot so it can reach the more high-scoring bricks at the top of the board. Looking at the results from Breakout, we see the same pattern again where the dueling Q network performs the best, and then the double Q network does outperform the deep Q network, which is what we expect. Space Invaders was the most difficult environment that we tested, and after 1 million frames of training, the agent is still struggling to dodge the incoming bullets, but it has learned to begin to shoot the enemies to score points. After 10 million frames of training, the agent has learned to shoot the enemy ships, and also it's begun to dodge the incoming bullets. However, it hasn't learnt its optimal strategy. Finally, after 20 million frames of training, the agent has learnt to dodge the incoming bullets from the ships, and also it's learnt the strategy of shooting the edges of the ships so that it gives the agent more time to shoot the remaining ships. This maximizes the score. Looking at the results for Space Invaders, we see a similar result where the dueling Q network performs the best. However, in this case, the deep Q network only slightly outperforms the double Q network. However, given more training time, since the double Q network is more stable, it would outperform the deep Q network. An interesting observation is that the dueling Q network learns at a slower rate in this environment. This may be because the dueling queue network uses a different architecture to the other two methods. Now we can look at some of the testing results from the trained models. We can see that in both Pong and Breakout, the dueling queue network performs the best, beating all of the other methods and the average human. However, in Space Invaders, we don't quite reach the average human score. This shows that it needs much more training time on the environment in order to compete with the human. Now we'll look at a visualization of the agent while it's playing on these different environments. Here we see the visualization of the game. On the left-hand side, we have the processed input from the emulator. That is the 84x84 pixel processed frame. And in the middle, we have the different layers of the convolutional neural network. It shows the activations of each of the filters in that layer. On the right-hand side, we have two graphs. One that shows the different actions and the associated Q values with those actions. The action we take is whichever action has the highest Q value. Underneath, we also see a graph which shows the plotted Q value for whichever action we take in that step. As we step through the environment, what we'll see is that the Q values start to increase gradually until we get to a point where the agent expects that we're going to receive some reward. At that point, the Q value will then have a sharp decrease, which we'll see now. We can see that as we scored the point, the Q value had a sharp decrease back down to its baseline level. That shows that the agent has learned to expect a reward once we score a point against the opponent. We can also visualize different layers of the convolutional neural network. In the different layers, we see different activations. And each of these shows a different feature that the convolutional neural network has learned to focus on. So as we step through the environment, we'll see different activations. A lot of the filters have activations just for the enemy paddle, but in some of the filters, we also see activations for the ball. The visualization also supports games like Breakout and Space Invaders, and additionally it could support any other Atari games that are trained using these different methods. In conclusion of this project, there was a few different achievements. First, we implemented a few different deep queue network methods, like double and dueling queue networks, which required different network architectures. Also, we made a visualization of the internal architecture of these networks, and we displayed them so we could investigate the internals of the networks and some of the interesting features that they produce. Also, we discovered the limits of these deep queue networks, such as how long they require to converge on different games using different methods, and we've shown that some of the environments are much more difficult to learn than others, such as Space Invaders compared to Pong. This is the conclusion of my screencast. Thank you for watching.